Hi everyone, this is the reflection video for the second part of POGIL 3 dealing with the t-test. In this day we did this on Monday, September 9th, and we looked at the other two cases of t-tests, the ones that we didn't see in the first 2 days of this POGIL assignment. And so in this reflection video I'm just going to go over the three cases, and I'm going to go through a couple of examples where we apply them, and some of the trick with these t-tests are to determine which is the right one to apply in each situation. And this is something, sometimes some keywords will give it away to you that you'll find in a problem or a situation. Other times, it's just something that you have to do practice a few times. So I'm going to go through a couple practice problems, ones that were at the end of the POGIL assignment, so you could look at those. I think they're number 30 and 33. And also, I'd recommend you taking a look at some of the practice problems I posted online and going through those. I'll post the answer keys to those later this week, just so you get a little experience working on them. Alright, so here are the three cases. These are the ones that you find in your book, and again, this is from Harris, Chapter 4, Section 5. There's going to be three cases, and this case 2, which is the most common case, is the one we went over a lot in class on the first 2 days of POGIL assignment. And case 1 and case 3 we went over today in class. So I'm just going to run through them all real quick. Case 1 is called comparison of measurements to a known value. And so the key that you're looking for is you're looking for something where there's a known value. This is sometimes considered if you're measuring a standard concentration or an agreed upon value, something along those lines. Those are keywords you look for. The things you want, just things that require special attention here. This is mu is the known value. Alright, so in this case what you're doing is you're looking at the difference for a bunch of measurements that you made, and you're comparing that to a known value, and this standard deviation, this is the standard of x, so it's x, right, x1, let's say. And this is just your number of samples, okay? So that's case 1, and again, keywords you want to look for things like standards, or things like known and agreed upon value, something like that. So we'll run through an example of that later. Alright, this is the second one. This is one that we saw a lot more frequently. This is called comparison of samples to means. And just so again, in this case you're looking at two sample sets with each with their own mean. You got mean 1 and mean 2. And then you have your standard deviation of 1 divided by the number of 1, right, that's squared. The standard deviation of the second sample set divided by the number of samples and sample sets squared as well. And so this is, I would say, the one that you see most commonly in literature. Just to give you an example, just pictorially what we're looking at. This is sometimes you'll see something like this, and you have some sort of variable here, your y value, whatever you want to call it, and then you have two samples, sample 1, sample 2. Each one of them has a standard deviation. Okay, so what you're trying to figure out is, are these two the same or different, right? So that's sort of how that looks, just sort of visually, the type of test you're trying to determine. Okay, so if you compare that to, let's say, in case 1, what you'd be looking at in this case, right? Let's say you have an absolute defined value of something, right? And that defined value we can put like here, right? You want to know, is this the same or different than that value? So we went through a couple of examples in class of where this might come into play. Let's say it's your sample set. You might be looking at something and you have a standard that's a defined value. You're trying to figure out if your measurement is actually accurate. And if you use a standard and you don't hit that accuracy, you might be incorrect. Another application of this, I think someone said you would be comparing it to like another experiment value. You're trying to figure out if your results agree with theirs. In general, the thing you want to make sure, though, is that your defined value here, this mu, does not have a standard deviation. Okay, so if you're comparing it to another experiment, that experiment has to be so precise that the standard deviation is essentially 0. The other thing that might be interesting, you might think of a situation like, let's say you're trying to determine, that sample, let's say some soil samples, let's say you have some regulatory limit that says you're allowed to, there's the soil with a certain pollutant in it may be considered dangerous after it's above a certain level. That may be what you're looking at here, right? So you take a bunch of samples of your soil and you're comparing it against this defined value. In this case, this defined value may be some pollution limitation, and you'll find out, are you above or below that pollution limitation. So those are a couple of different examples of where this might come into play in real life. And again, this is your case 2. And case 3 is where the real key here is paired measurements, okay? Paired measurements, okay? So a lot of the examples we show in analytical chemistry are situations where you're measuring the same sample 2 different ways, right? And so you want to compare and see if those results are the same. But what's really key here is that these are paired measurements. And you're going to see that in an example that we run through. Okay, so here's an example. This was from number 3 in your assignment, or number 30 in your assignment. Question is, all right, so Bob and Bill make repeated measurements of the amount of iron in 2 iron ore samples. Here's Bob's measurements, here's Bill's measurements. Then Bob and Bill learned that their samples are from the same source and that the accepted value is 20.009%. Are Bob and Bill's mean significantly different from the accepted value? Alright, so the key word that you should be popping out here, even though you have 2 different populations, you may be tempted to compare them to each other, but the key word here is accepted value. Alright, so you have an accepted value, but different than the accepted value, right? And so that's sort of a key word that's going to key you into this being case 1. Okay, so case 1, again, that's this one here, comparison of measurements to a known value. Alright, so we're just going to run through a quick calculation on that. Just to show you one of these examples. In this case, we're going to start with Bill's measurements, okay? So if we're thinking about summary statistics for these, you have your average, call this average for Bill. Oh, no, sorry. Let me fix it. I'm actually going to do Bob's here, so I've got that already calculated out in front of me. Let's see. There you go. Bob. All right. So the mean of Bob's values here, what you get from this table, is 20.19%, and the standard deviation from Bob's measurements are 0.06%. And then something else you want to bear in mind here, so n, right? This n is the number of measurements from Bob only, okay? And that's 1, 2, 3, 4. Right? And another thing we want to look at is this, because we're using case 3, we have an accepted value, and that's mu. And mu, its accepted value is 20.09. 20.09%. Our degrees of freedom here, call this NDF. Our degrees of freedom is the number of averages. In this case, there's 1 average minus the number of total samples. Our number of total samples minus the number of averages. This is 4 minus 1 minus 3. And so from this, we want to know your critical t value, because you're going to be comparing everything to that, t critical. So in general, if I don't tell you what confidence interval we're talking about, the generally most common one is 95%. So if it's not specified, that's what you should assume. And so we have 3 degrees of freedom. So 3 degrees of freedom. Our t critical value is 3.182. Okay. All right, and again, we're using case 3 here. And our case 3 equation, t calc equals the difference between average value and mu over our standard deviation of x times the total number of samples, square root of total number of samples. So at this point, we really just need to plug our values in. It's pretty easy. So our t calc equals absolute value 20.19 minus our mu, which is 20.09. These are absolute value bars. That is all divided by your standard deviation, which is 0.06, times the square root of the number of samples, which is 4. So you calculate this out, and you get t calc equals 3.33. We'll see here, right here, T-calc and T-critical. T-calc is greater than T-critical. Therefore, these are statistically different. So what we're seeing here, right, is that we have this accepted value, 20.09, and Bob is measuring 20.19, and he's significantly off. So what we'd probably come to conclude from this is that there's something wrong in the method that Bob is doing to determine this. And so I'm not going to go through and calculate Bill's here, but you guys can do it on your own. And just hopefully you'll find out that Bill is not significantly different from the mu value, the accepted value. Okay. All right, so that's an application of case 3 here. I'm on that job. All right, and that's case 1. Sorry, I'll fix that. So let's erase this guy. All right. What I meant to say was that was case 1. Sorry, these numbers are sort of arbitrary, these case numbers. The important thing is that you're using the right equation here. Okay. All right, so example number 2. This one comes from number 33. Right. So this one is, so both of these examples you'll see are sort of meant to be a little tricky. They're not super obvious. But if we go through this one, okay, 8 patients are treated for hypothyroidism using new drug therapy. Their serum calcium levels were measured before and after treatment. All right, so you have patient 1, 2, 3, 4, 5, 6, 7, 8. You have untreated and treated. And so the question is there a significant increase in their calcium levels? And so you might be tempted to use case 2, the comparison of means. But what we're actually watching is the difference for each individual patient in one condition versus another condition, right? So this would be considered a paired measurement. Okay, the sample is the same, it's being measured at 2 different times. And so in this case, we're going to be using case 3. These are paired measurements. All right. This is something that would be pretty common in clinical studies. Oops. What you're looking for is a before and after, and you're tracking that individual patient. All right. Where this would be different if these weren't individual patients, but they were just randomly selected people that were either treated or untreated. But because we're watching the same patient in 2 different conditions, these are considered paired. Okay. So in order to determine this, we use case 3, which, if you remember, case 3 uses the differences, the average differences divided by the standard deviation of the differences times square root of the number of samples. So what we do is we make another table here, and you get your differences between treated and untreated, and we're trying to find out if these differences significant. Okay. So here we go. We use case 3 in this case, and so the sort of the summary statistics we're caring about in this are all dealing with the differences. All right. So we're looking for the average I'm out of space here. The average differences. So here we go. So the average differences, all right, which you just take by averaging all of these guys here. Your average difference ends up being 0.105, and then the standard deviation of those differences. Okay. So you want to make sure that it's not the standard deviation of all these samples, it's just the standard deviation of these differences, and that ends up being 0.10. Hopefully you guys find the same answers when you go through it on your own. And the number of samples, in this case, is not the total number of samples, but the total number of patients in this case, right? So the total number of paired samples. So even though you have 16 measurements overall, you really only have 8 paired measurements. So that's 8. Okay. Your degrees of freedom in this case are just going to be the number of samples which in this case is 8, minus the number of averages. We only have one of those, so your degrees of freedom are going to be 7. So then we want to look through our table here. In this case, again, I don't specify, so we're going to assume it's 95%. You're looking at the 7 degrees of freedom level, so it's 2.365. So our t-crit equals 2.365. Alright, and again, we're using this equation, which is case 3. And that is our t-calc equals the absolute value of the average differences, in that case, value there, divided by standard deviation of differences, times the square root of the number of samples, paired samples. Okay, so we can just plug these values in. I'm trying to make it a little clearer by changing the pen color. In this case, our t-calc equals 0.105 divided by 0.100 times the square root of 8. Plug these numbers in, you get your t-calc to equal 2.97. Alright, in this case, again, now our t-calc is, again, larger than our t-crit. So our critical value of t. So that means, therefore, these treated are significantly higher. Alright, so this is a real type of application you're going to see these in. Alright, so what we're looking at is untreated patient is given treatment, their calcium levels increase, and we have shown statistically that, in fact, this increase is significant. So, again, I recommend you guys taking a look at the practice problems in 4-5, the practice problems I posted online, and giving them a try. I'll post the answer key set later this week, and hopefully you are able to figure out which t-test to use and which method. And so on the POGIL on Wednesday, we're going to pick up with POGIL 4, which is dealing with the F-test, which is a test to determine if standard deviations are significantly different. See you then.